Alright, in this video we're learning about kinematics, and kinematics is quite a long topic in calculus, but we'll have lots of practice to get used to it. Essentially, this is the physics bit of the calculus. But if you don't know physics, don't worry, because, well, I didn't do physics either, so I'm going to tell you all in maths terms what's going on, rather than using a whole bunch of physics assumed knowledge. So essentially, we've got these three functions: displacement, velocity, and acceleration. Displacement tells you where you are. Velocity essentially tells you your speed, except it also gives you a direction with that. And acceleration tells you how quickly you're speeding up or slowing down. So you differentiate each one to get the next. If you differentiate your displacement, you get velocity. If you differentiate velocity, you get acceleration. And the units go like that. So they're meters, then meters per second, then meters per second per second. But yeah, speed is something worth mentioning as well. It's just the actual speed. So essentially you take the velocity, and if it's negative, you make it positive. And in general, with the signs like negative or positive, negative usually means left and positive usually means right. Or if you're dealing with up-down problems, positive usually means up and negative means down. You then got this common language. So there's a huge bit of info there, but basically most of the questions just look like this. So we'll work through some examples. What we're going to do here, t cubed take 3t plus 1 is the displacement. And that's given in the question. So this is going to be part A. They want us to find the velocity, which is going to be the derivative. And then the acceleration, which is going to be the derivative again. Done. That's part A completed. Part B is going to be to find the initial conditions. So with the initial conditions, they want all of the initial conditions. So S of 0, V of 0, and A of 0. S of 0 is 0 cubed, take 3 times 0 plus 1, which is 1 meter. Sorry, they're in centimeters, not meters for this question. 1 centimeter. V of 0 is, plugging 0 in here, 3 lots of 0 squared take 3, which is minus 3 centimeters per second. And A of 0 is 6 times 0, which is 0 centimeters per second per second. So how do we describe this? What we can say is that I think it's a particle. The particle starts 1 centimeter right of the origin, moving with speed 3 centimeters per second. I might actually go velocity left. So how you can tell it's right or left, the first one was right because it's positive, and the second one was left because it's negative. And not speeding up, slowing down. Because the acceleration is 0. Now the acceleration won't stay at 0, the acceleration will change, but currently it's not speeding up or slowing down. So part B is done. Describe the motion at t equals 2. So we need to work out S of 2, V of 2, and A of 2. So that is 2 cubed take 3 lots of 2 plus 1, which I believe is 3 centimeters. V of 2 is going to be 3 lots of 2 squared take 3. So that gives me 9 centimeters per second. And A of 2 is 6 lots of 2. Which is 12 centimeters per second per second. Now I'm not going to make the same mistake as last time. I'm actually going to type this. The particle, after 2 seconds, the particle is 3 centimeters right of the origin, moving with velocity 9 centimeters per second right, speeding up with acceleration 12 centimeters per second. Done. So make sure you describe all three and make sure you give units for all three. Part D is find the position of the particle when it changes direction. So we can do that. Now, change direction happens when the velocity is 0. And hopefully that should make sense, because if you have something that's like moving around, like the velocity is 0 there, because it's not moving right, it's not moving left, it's sort of just neither moving right or left. And this is also like reverses here. This is what this table is trying to tell you. Yeah. So what we can do is set velocity to 0. 3t squared take 3 equals 0. Now, it wouldn't hurt to have sign diagrams of everything, although... I actually missed that in part A. Sign diagrams of each term. So I might actually just squeeze these in here. Yeah. This is why it's important to read your questions. So one thing we can do to solve the sign diagram for S of t is to actually just set it to 0. So t cubed take 3t plus 1 should equal 0. And we can actually just use the equation solver on the calculator to do that. You can use polysolve on a Texas to do that. So this is degree 3, 1 lot of t cubed plus 0 lots of t squared, take 3 lots of t plus 1. Solve that. 1.532, 0.342. And minus 1.879. And probably the easiest way to get the pluses or minuses is literally just to graph the function itself. So back to menu, we'll graph this. X cubed take 3x plus 1. Have a look at what this is. So if you're doing the sign diagram for the position itself, you need to think about whether it's above or below. So these 3 numbers we found are our x-intercepts there. So it's going to be going underneath and above. So we're going to get minus, then plus, then minus, then plus. This sign diagram is based off our position itself. So I'll give myself a little bit more room. All right. So next sign diagram we need is the velocity. So you put t and the velocity there. So it looks like it's going to be going up, down, up. The velocity 3t squared take 3. What you can do is actually put that in polysolve to do your sign diagram. So polynomial, I mean, it's just a quadratic. We should be able to solve it using like the quadratic formula or something, but if you're doing sign diagrams, it's kind of hard enough without having to think about quadratics. 1 and minus 1 we'll put on there. And make sure you line these sign diagrams up. So 1 goes there and minus 1 goes there. So the 0.3472 on the S sign diagram needs to lie in between there. The velocity is going up, then down, then up based on the slope of that graph. With the acceleration, t and acceleration, 6t would be 0 here. Acceleration is positive to the right and negative to the left. So those are your 3 sign diagrams. And particularly with your velocity, we want to do like minus 1 and 1 is where that equals 0. Now, one thing that I have to fix up about these sign diagrams is they shouldn't actually have these bits to the left here. So all that stuff over there can actually go away, because your velocity problems always just start at 0. So similarly, all that stuff over here can go away because it starts at 0. And same with acceleration. all of that can go away because it starts at 0. So realistically, with your sign diagrams, you only want to draw them from 0 going on to the right. That's just in kinematics problems. Anyway, so to solve 3t squared, take 3 equals 0. We just did it. So t equals -1 or 1, but t is positive, so t equals 1. Let's see, that's when it changes directions at t equals 1. And I think, did ask for where it changed directions as well. Find the position of the particle when it changes directions. So s of 1 is going to be, and what we can do is actually just look back on our graph. Rather than trying to sub in the number, what we can do is trace at 1. So trace at 1, and you get -1. So 1 equals -1 centimeters. The particle turns around after 1 second, and its position is 1 centimeter left of the origin at this time. Done. All right, for part E, draw a motion diagram of the particle. So essentially what you want to do is look at your initial condition. So it starts 1 centimeter to the right, and the motion diagram looks kind of weird when you first see it. It's kind of looks like a sine diagram, but you've got s of t there. Displacement is actually along this axis here, so it will go negative 2, 3, 4, -1, -2, -3. So we know that this particle starts at 1 centimeter to the right, so we're going to draw that in here. And then we know that it just continues going left, so it's traveling left here until it hits this -1 centimeter where it turns around. And then it goes to the right again. And then you can label this bit with t equals 1 if you'd like. So that's the particle's motion diagram. And what the motion diagram should look like is if I take my graph and I go V window, but I only start at 0. So it goes like down and then up. You sort of have to flip your head on the side and then mirror image it, and that gives you your motion diagram. F, for what time interval is the particle's speed increasing? So what I'll do is I'll take these sign diagrams again. We'll use those. So F, speed increasing. So essentially, the speed is increasing if the velocity and acceleration sign diagrams are the same sign. So I think it says something like here, like there. So if they're both positive and negative, then the speed is increasing. And if they're opposite, the speed is decreasing. So if we look at our sign diagrams, you can see for all this range here, and this is why it's important to line them up, speed is decreasing because we have plus and minus. But for all this range here, speed is increasing. So therefore, speed is increasing for t greater than 1 second. All right, part G, what is the total distance traveled from time t equals 0 to t equals 2? So you can see that it sort of went from 1 centimeter up to 3 centimeters, but it's a little bit tricky. So G, total distance traveled from t equals 0 to t equals 2. So what I'll do is I'll actually use the motion diagram again to help. And this sort of looks like your graph. So we know that at t equals 2, the particle's at 3 centimeters. So I'm just going to label this bit with t equals 2 here. Now, I might color code these. T equals 0 to 1. The distance is 2 centimeters because it's sort of that range in there. T equals 1 to 2, the distance is 4 centimeters because it's sort of this range in here. So yeah, if you just looked at like the total difference, so the displacement difference would be like from 1 to 3, it would be 2 centimeters. But what we can say is here that the total distance is 6 centimeters. And distance doesn't have a direction. Distance is just like total distance. And that's just by literally adding them up. If we wanted, the question doesn't ask for it, but if we wanted the total change in displacement, that would be 2 centimeters, right? Because the displacement function has gone from 1 centimeter up to 3 centimeters, even though it didn't take a direct path there. So yeah, you can see that it's changed from 1 up to 3 in that process. So it's gone 2 centimeters right in displacement, but the actual distance that it took to get there was it went 2 and then another 4. So that is 2 and that is 4. So yeah, this topic is quite big, but basically this is everything we can ask you about kinematics, pretty much. So if you learn sort of the answers to this style of question, you'll be pretty much fine for these problems.